Once hypotheses are set based on desired dependent variables, the actual process of data collection can begin. However, raw data needs to be converted into a form that you can actually use. In this video, our focus is on organizing qualitative or categorical data, so patterns become visible. We will cover basic ideas like data types, cross-tabulations, and contingency tables, then use an example to interpret results. It is not about learning the formulas, as much as understanding how simple data tables can be interpreted to extract business meaning and determine a course of action. Raw data is simply a list of individual observations, and by itself it rarely tells a clear story. Once we organize that data into tables, we start to see patterns and differences across groups. That structure allows us to ask focused questions, such as what factors in the data affect changes in our variable of interest. In practice, we can use simple tables and visualizations to look for patterns and possible relationships before we formally test our hypotheses. Organizing data is the bridge between collecting information and making a decision. Luckily, modern software and AI tools can make the actual process of organizing data easier than ever before. But if you aren't careful about checking how it has been organized, those very tools are capable of capturing patterns where none exist and can mislead your decision-making process. There are two primary types of data, qualitative and quantitative. Qualitative data uses words, labels, codes, or even numbers to describe categories, such as hair color or satisfaction levels. Quantitative data uses numbers that have real numeric meaning, like sales dollars or number of visits. Within qualitative data, some categories are just names, while others have an order. Understanding which type you are working with changes how you summarize, present, or visualize the data, and what kinds of comparisons or models make sense. For business interpretation, this prevents you from treating labels as if they were precise measurements. The biggest caution point is that in qualitative data, numbers can be used to show preference order, which we will discuss next. In qualitative data, a nominal scale uses categories that are simply names, such as black, brown, red, blonde, or gray for hair color. There is no ranking built in, so one color is not higher or lower than another. On the other hand, an ordinal scale does introduce an order, such as rating satisfaction levels from 1 to 5. With ordinal data, a higher number represents a higher level, but the numbers themselves do not represent exact amounts. For example, a satisfaction of 2 is not double a satisfaction of 1, and 4 is not double 2. Thus making claims like, a satisfaction value of 4 is double the satisfaction value of 2, is false. It just means that a person with satisfaction level of 4 is more satisfied with their situation than a person with satisfaction level of 2. In qualitative data, assigning numerical power to the numbers can be misleading. When interpreting ordinal data in business, you should talk about higher or lower levels or ranking, not about numeric differences or ratios. Because qualitative data is based on categories, its meaning often comes from how frequently each value appears. Counting how many people fall into each category gives you a basic frequency distribution. Converting those counts to percentages lets you compare groups that are not the same size, which is essential in real-world business populations and samples. When you present these results to stakeholders, percentages are usually easier to digest than raw counts. This simple step turns a long list of responses into a compact story about how variables in your sample behave. In the table above, we can see how we can compare frequency of seatbelt use by males versus females, even though the samples are of different sizes, by using a frequency distribution table and calculating the percentages for each category. This also allows us to quantify or find numbers of value from data that is otherwise qualitative. A cross-tabulation is a table that shows how two variables relate to each other. It is especially useful when at least one of the variables is categorical, such as sex or satisfaction level. Each cell in the table shows how many observations fall into that combination of categories. For example, males who always wear seatbelts. Testing hypotheses of whether sex is related to seatbelt use would require a chi-square test, which isn't a part of this certificate. However, the table alone already gives key insights. Consider data collected on 900 drivers in the USA, where we record two things for each driver: their sex and how often they use seatbelts. Sex is a categorical variable, and seatbelt use is an ordinal variable, so they are ideal for a cross-tabulation. The resulting table shows how many males and females fall into each usage category. This single sample-based table becomes a compact picture of seatbelt behavior across male and female drivers. For business leaders, learning to read this table is often enough to spot patterns worth acting on or exploring further. Row percentages use the total of each row as the base and look at how that row is split across columns. In our example, the row for males sums to 320 SIPs, so each seatbelt category for males is divided by 326. From this, we see that 105 out of 326 men, or 32.2%, always wear seatbelts, 19.9% mostly wear them, and 18.1% never wear seatbelts. Row percentages answer questions like, what percentage of each sex falls into which seatbelt use category? For business decisions, this points to which segments might need targeted messaging or different interventions. Notice that these numbers are the same as we got when we created the frequency distribution in the earlier slide. Column percentages start from each column total and ask how that column is distributed across rows. In the seatbelt example, there are 405 people who always wear seatbelts. Of these, 105 are males and 300 are females. This translates into 25.9% of always users being male and 74.1% being female. Column percentages answer questions like, what is the percentage of males and what percentage of females in each seatbelt usage category? In business terms, this tells you who is in a desirable or risky behavior group, guiding where to focus resources or campaigns. Total percentages use the grand total of all observations as the base. Here, each cell is divided by 900, the total number of drivers in the sample. For example, the 105 males who always wear seatbelts represent 11.7% of all drivers. When you sum by sex across the table, the total percentages match the sex distribution, and when you sum by seatbelt use, they match the usage distribution. These percentages show the relative size of each group in the full population, which matters when you evaluate the overall impact of any behavior. Once you understand row, column, and total percentages, you can begin to interpret cross-tabulation patterns in a business context. Comparing rows helps you see how behavior differs between groups, such as males and females. Comparing columns tells you which groups dominate a particular behavior, such as always wearing seatbelts. Linking these findings to actions, you might design different messages for segments with low compliance, or study why certain groups behave more safely. Finally, the patterns you see can be turned into formal hypotheses, which you can test with appropriate statistical methods when needed. We have seen how turning raw data into organized tables makes complex behavior easier to understand. By separating qualitative from quantitative data and recognizing nominal and ordinal scales, you avoid misinterpreting what numbers really mean. Row, column, and total percentages provide three complementary views: within group behavior, group composition, and overall population impact. When you read a contingency table, focus on the business questions it answers and the interventions it suggests. The real power of these tools lies in using them to support clear, data-informed decisions, rather than simply producing more calculations.